Okay, so we're going to be doing our second lesson in gas laws, and we're going to learn about two scientists and the laws that they are accredited to. So after today, I want you to be able to explain the effect on gas properties using Boyle's and Charles's laws, and I want you to be able to calculate an unknown pressure, temperature, or volume by solving algebraically. So basically, this first scientist, Robert Boyle, he was the first person to study pressure and volume relationships of gas. So all the way back in 1662, Boyle proposed a law that describes this relationship. So basically, as the volume decreased, okay, so he decreased the volume, pressure is increasing going to the right. So as the volume decreases, the pressure increased, okay? So he noticed this relationship, and he came up with this law that for a given mass of a gas at constant temperature, so basically same mass, same temperature, the volume of a gas varies inversely with pressure. So the lower the volume, the higher the pressure is basically his law. So he has a formula to describe this relationship. So the pressure 1 times volume 1 is equal to the pressure 2 times the volume 2. So pressure can be in any unit, atmosphere, kilopascals, or millimeters of mercury, but they must match. So if in the question it doesn't give you the same pressure units, you need to convert one, more preferably the one that the question's not asking for the answer to be in. So for example, if it gives you atmospheres and millimeters of mercury, and it asks for millimeters of mercury, it's probably best to convert the atmospheres to millimeters of mercury, since that's what the question is asking for. And then volume can be in any units, usually liters or milliliters, but again, they must be the same. All right, so the first question, it says a gas has a volume of 30 liters at 150 kilopascals. So we have our equation, P1 V1 is equal to P2 V2. So we have this equation. So a gas at a volume, so our P1 V1, P2 V2. Okay, so we're going to read the question and fill this out. So a volume of 30.0 liters at 150 kilopascals. Okay, what is the volume? So we need to know what the volume is. There's our unknown of the gas at 0.252 atmospheres. So now what we need to do is just plug these numbers in. Unfortunately, they didn't give us the exact same units for pressure, so we need to convert. The question is asking for volume of gas in atmospheres. So it's asking for this unit. So might as well go ahead and save us time and convert this to atmospheres. And I always use dimensional analysis. Use whatever you're comfortable with. So, sorry, on the test, I'll give you a conversion chart. But for every 1 atmosphere, you have 101.3 kilopascals. Okay? So just to convert that, you have 150 divided by 101.3. Get your mouth off the desk. That's gross. 101.3. And you have 1.4807, which we just need 3 significant figures. So 1.48. These units cancel. Atmospheres. So we've converted. So now we have our units, and we just need to plug them in. So we have P1 V1 equals P2 V2. We need to answer this. So we're just going to divide it all by P2. So then the equation becomes P1 V1 over P2 equals volume 2. So we're just going to plug in numbers now. Pressure 1 is 1.48 times 30.0 divided by 0.252. So we're going to put that in the calculator. So 1.48 times 30 divided by 0.252. And our answer is we need 3 significant figures, so 176. And liters will be our answer. 176 liters. Okay. Sorry, 180. 1.5 atmosphere. We just messed up our significant figures up here. So we should have had 2 significant figures here. So that's my fault. Okay. Moving on, Charles's law. Charles's law Boyle's law was a pressure volume relationship. Charles's law is a temperature volume relationship. So he studied temperature on volume of a given gas. Of a gas at constant pressure. So pressure stayed the same, temperature and volume are the ones that changed. So about 100 years later, I don't know why it took 100 years for him to propose this law, but he described this relationship with this graph, okay? So as as temperature increases, the volume also increases. So for a given mass of gas at constant pressure, so that means mass is the same, pressure is the same, the volume of the gas is directly proportional to the temperature in Kelvin. So basically his, his formula is volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. So volume, again, is in a unit, usually liters or milliliters, but they must match. Temperature is always in Kelvin. There's no variation from that. So let's do a quick example. So Charles's law, remember his formula is volume 1 over temperature 2 is equal to volume 2 over temperature 2. I'm so sorry, that should be... I don't even know if I said the right words, but it should be temperature 1. Okay, so the question, so we are going to be given 3 out of 4. Volume 1, temperature 1, volume 2, temperature 2. Okay, so a gas has a volume of 4.0 liters, so 4.0 liters at 27 degrees Celsius. And what is its volume at 153 degrees Celsius? So we need to find that out at 153 degrees Celsius. So always remember the rule prior says that the temperature is always in Kelvin, okay? So we just add 273 to the temperature. So here, the first temperature is 27, so you add 273, okay? So 300. So that's 300 Kelvin. And then same thing here. We're going to add 273 plus 153. We have 426. Okay, so there's our variables. So we're just going to plug them in. So we need volume 2 to be on its own. So the way we can manipulate this equation is by multiplying T, the second temperature, on both sides, which will give us the equation T2 times volume 1 over temperature 1 equals V2. So that equation we can use and plug in these variables. So volume 2 will equal to temperature 2, which is 426, times volume 1, so 4.0, divided by temperature 1, and we just plug those in to the calculator and we should have our answer. So 426, you cannot see that. So 426 okay. So the answer, 5.68. Our lowest significant figures is 1, so we need to round that to 5.68, round it to 6, I guess. Let me see if I'm doing that. Yeah, I guess so. We'll round it to 6. Okay, so that's 6 liters. That's our answer.